Hello students, this is Professor Chalai, and in this video we're going to go over some of the things that you need to know for your FeSCN2 Plus Equilibrium lab. In this lab we're going to react iron 3, right, with thiocyanate, that's SCN, to give this complex here, let's put some aqueous signs, to give this complex here FeSCN2 Plus, aqueous. And we're trying to find the equilibrium constant for this reaction. So that would be our products over at equilibrium over our reactant concentrations at equilibrium like this. Okay, so this is the aim of the whole lab. Now, to be able to calculate these concentrations, we can actually track the concentration of this complex ion because it has a nice vibrant color that absorbs at around 455 nanometers. There we go, nanometers. So we can track the progress of this experiment by tracking the absorbance of this compound. But before we can do that, we don't need the absorbance, right? We need the concentration. So before we can do that, we need to figure out how absorbance will relate to concentration anyway, or Beer's law. And so that's what we're going to do with set 1 of this experiment. And this is beakers 1, 2, and 3. So in set 1, our aim is only to relate the absorbance to concentration of this complex 2 plus, right? And just as a warning, for this set 1, you need to use the high concentration of iron 3. Right? That's very, very important. And the reason for that is, in this reaction, if this iron 3 concentration is very, very high, it means our thiocyanate ion concentration would be limiting. Your SCN minus is limiting reactant. Right? And what this means is it will push the equilibrium completely to the right and use up all of your SCN minus, or most of your SCN minus reactants. And so you'll end up in a situation where the starting concentration of your thiocyanate, initial, or 0 for starting, will be approximately equal to your complex ion concentration at equilibrium. Let's use I for initial. Right? So you use a high concentration of iron 3, pushes the equilibrium all the way to the right, and uses up all of the thiocyanate that you have. And so by doing that, we can figure out what concentration of iron thiocyanate that we have, and then relate that absorbance, the concentration to that 3 absorbance. So then the question is, how can you figure out what the initial concentration of thiocyanate is? Right? And the answer to that is you just calculate the moles of thiocyanate and divide by total volume. So let's say you add one of the beakers, you add 2 milliliters of 0.2 molar iron 3 and 1 milliliter of, let's say, a 0.0020 molar thiocyanate, right? Notice this is the high concentration of iron. And let's say 7 milliliters of water, such that your total milliliters here is 10.00 milliliters total, right? To figure out what the concentration of thiocyanate is, and therefore the concentration of thiocyanate at equilibrium, is you calculate the moles of SCN, right, by basically using your volume of SCN, 1.00 milliliters, convert that to liters, and then multiply that by the concentration. I think this is 2 zeros, moles over liters, which will give us 2.00 by 10 to the minus 6 moles. And then if you want the concentration, you take that number of moles and you divide it by the total volume, which is 10 milliliters, but of course we want this in liters. So moles over liters will give us a concentration of 2.00 by 10 to the minus 4 molars. So this is your concentration of thiocyanate to begin with, which in this first set is also the concentration of your iron thiocyanate at equilibrium, approximately, but it'll be enough for now. And so that will be true for sets 1, 2, and 3. And so for each of these 3 solutions, you'll make them, calculate the concentration of your iron thiocyanate at equilibrium, and then for those 3, you make a plot of absorbance versus concentration in molars, right? And your 3 points will lie somewhere on the plot, and then use the 0, 0 point as part of your plot as well. And then this should give you a y equals mx plus b straight line curve, right? So from this curve, we'll get the information that we need to use for later, because later we'll need to use the absorbance to find the concentration, right? We'll need to be able to find the concentration x from some absorbance y. Okay, the second part of this experiment, right, which we call set 2, and this will be beakers 4, 5, and 6, we need to use the low concentration of iron 3, right? And that way, the concentration of iron 3 and thiocyanate will be roughly equal to each other, and that could set up a nice equilibrium that we can do. And then in each of these 3 trials in set 2, you'll need to create an ice table, right, where we'll have our iron 3, or thiocyanate, and our iron thiocyanate complex here, the product, right? You'll set up your ice table. There we go. Initial change equilibrium. And this initial concentration of iron you'll need to calculate based off of the initial concentration. Initial concentration of thiocyanate you'll also need to calculate as we did earlier. And let's assume 0 products, right? And we do, whoops, this is negative x. I had that correct. Positive x. And so we'll have over here, this is equal to x. This is equal to whatever that calculated initial concentration is minus x. And same over here, right? But before we know what these are equal to, we need to solve for x. But we know that x here, whatever this concentration at equilibrium is, we can get from absorbance. So we'll stick this in our spectra vase and get the absorbance for it, and use the equation y equals mx plus b from our absorbance versus concentration graph up here, and plug in absorbance for y, right, and solve for the concentration x, right? So we'll have y minus b over m, which will give us the concentration x, the same x that actually fits there. We'll know x, which means we can also calculate what goes here and here for equilibrium concentration, and then we can calculate Kc by using those 3 values here. And that's it. That's the gist of the lab, right? We'll basically create a calibration curve in set 1, and then set 2, we'll run this trial 3 times to figure out what the equilibrium is. Just some things to like pay attention to, right? Make sure you label things carefully. Label beakers carefully, right? Because you're dealing with 2 different concentrations of iron. You don't want to mix them up, right? You're using one type of concentration set 1, one concentration set 2. So I guess, pay attention to which iron 3 you use, right? And the third point here is record exact amounts of volume that you use, right? So you will have suggested amounts of, for example here, you'd have suggested amounts of each of the 3 components, your 2 reactants and water. But, if you use, instead of, let's say, 1.00 milliliters, you use 1.05 milliliters, then record exactly 1.05 milliliters to use in your calculations later. Record the exact amounts of volume that you use. The fourth thing that I want you to pay attention to is this is an equilibrium lab, right? unlike our previous labs where it was kinetics based, and so speed was important because you had to check, get the initial rate of the reaction before those rates change. For equilibrium, we're waiting until the reaction, comes to an equilibrium. So you need to wait, right? This is a patience game. Wait until, some time has passed before running your samples, right? You want to make sure it comes to an equilibrium first before you go measure it in a SpectraVis. And then the last thing for cleanup, put all waste in the hood. There'll be a special container in the hood to put all the waste in. All right, I will see you in lab. Bye.